Hey everyone, so today we are going to talk about one of the very important function which is called as a Dirac Delta function, or many times also an impulse function. Okay, so we are going to see what is this function. We are going to study its properties, like we are going to see what is the integral of the function, what is the derivative of this function. I have not written the derivative, so like the derivative of a unit step function is nothing but a delta function. Not the usual derivative. I will spend some time on this maybe after some time, but yeah, so once we have a function, we are going to study what is integral and derivative of the function. We are going to see the Laplace of the function, and at the end this one nice property one can prove using mean value theorems for definite integrals. Okay, so this is what we are going to discuss today, and this is one of the very nice function that people will encounter when they model the situations. Situations like what? So I would like to say, suppose if there is a room, there is a pin drop silence in the room, and someone just comes and just hit a hammer, bam, and then again there is a pin drop silence. So like there wasn't just an impulse at that point, and then again everything is quiet. Or it's raining normally, and just for a second there is a huge lightning just went off, and then again it's raining normally. So when things are going smoothly and in between something happens, there is a short, then such function comes into picture when you do the modeling. Like the current is flowing, suddenly sometimes there is a spark in the current, and then again the current is flowing normally. So whenever such things happens, and when you try to model and when you want to study, then you will see this thing in the picture, and therefore it's important to study this. Okay, now once you study calculus and once after that you see this function, people say that this is a function. First thing you think that is it really a function? Because when you study calculus, your teacher will always say f is a function. What is a function? For input there is an output. Okay, so output should be defined, then only is call it as a function, right? If the output is not defined, it's not a function. Or you don't take those points in the domain, because for those points you are not getting the output. Okay, so that's how you define the function and domain and everything. And now when you see this, they call this as a function. At a is infinite and not equal to a, it is 0. And now obviously you will think, why infinity? Then if infinity is coming here, is this really a function? Well, so whatever you have studied in calculus is not wrong. Here this is a very special function, and therefore many times people also call this as a generalized function. Or in future when you study probability, this is one of the type of a distribution. Okay, so infinite values are allowed. Okay, so there's one justification I would like to give, that okay, we call this as a generalized function. So don't think that whatever you have studied in calculus or whatever we have taught you in calculus is incorrect. No, that's correct. But yeah, this is a special function where it is taking infinite value. So therefore you also call this as a generalized function. Okay, and in any other standard books, if you see, people directly state the results. Okay, which obviously I don't like. So I'm going to give you the justification for this. I will try to convince you. Okay, so I hope you get convinced. If not, you can ask me in the comment section. Okay, now this is the function and this is the integration. Now to prove that the integral is 1, what we are going to do is, we are going to construct a sequence of functions that will approach to the delta function. Okay, and then you have studied sequence of numbers approaching to a number, right? Today we are going to construct sequence of functions that will approach to this function, and then we will take help of those sequence of functions to find the integration, Laplace, and these two things. Okay, so let us try to construct that function first. Let us try to construct the sequence of functions that will approach to the delta function. Now, even before that, so if someone is writing delta t means what? It is infinite at t equal to 0 and 0 t not equal to 0. Okay, so at 0 there is a spike, and then again everything is 0. Okay, so this is what it is defined. Now when people study differential equations or Laplace, that time they only concentrate on t greater equal 0. but then you can define this for t any real number. Okay, like you can say t belongs to R. So in that case it is 0 everywhere. At 0 there is a sharp, and again 0 everywhere. Okay, so from minus infinity to infinity also delta function is defined. Like from minus infinity to 0 it is 0, at 0 it is infinite, and again it is 0. Okay, but even many people just play with 0 to infinity, they don't take t as a negative time. Okay, people always play with positive time parameter, but when you play only with theoretical stuff, then taking negative t is allowed. Okay, like if you build a time machine where you want to go into the past. Okay, so t negative is allowed in such scenarios. Okay, just joking, but yeah, t negatives are allowed in theoretical part. So that's why you may also see the definition of delta defined over the complete real number. Okay, so it's okay, doesn't matter. Before 0 also I am taking 0 only. Okay, so that's one thing. And when I want to say delta of t minus a, okay, so here there is no a, means because here my a is 0 and my a is non-zero. That means what? If a is somewhere over here, there is a spike at a and 0 everywhere. Okay, so there is a spike at a and 0 otherwise. So this is how one defines the Dirac delta function. Okay, so this is one point I want to clarify. So don't get confused. Even if you see this as the domain, it's okay, and if you see this as a domain, then also it's okay. Properties do not change. Okay, so that's not a concern because it's 0 only, so it doesn't matter. Okay, now let us try to construct the sequence of functions. Now what I'm going to do is, you define fk of t minus a. You define this as 1 by k in the interval a less equal t less equal a plus k and 0 otherwise. Other than this interval, you define the function 0. Now let us try to visualize this. Okay, now suppose when my k is 1, so my suppose a is here, suppose my k is 1, so what is f1 of t minus a? Or let me first write for in general. So this is a to a plus k. In this interval, the value of the function is 1 by k. So for these points, my function is taking the value 1 by k and it is 0 everywhere. Okay, now this is the function I am defining in general for k. Now if you observe, when I take limit k going to 0 of this sequence of function, when I take k going to 0, where these functions will approach. So like for example, when my k is 1, so this is the value from a to a plus 1, the function is constant function 1, and then from here 0 everywhere. When my k is 1 by 2, when k is 1 by 2, so this is a plus 1 by 2. So from a to a plus 1 by 2, when my k is 1 by 2, the output is 1 upon 1 by 2, which is 2. So it is taking the value 2. So it is 2, and then again from here is 0 everywhere. When I take 1 by 3, so from a to a plus 1 by 3, my value will be 3, and then from again here everywhere it is 0. So you keep on doing like this. So like if I erase this part, what is happening is this is becoming smaller and smaller. So like here it is this much value, and from here again everything is 0. Okay, so as you can see, as my this was k, as k approaches 0, your a plus k will approach towards a, right? And this sequence of functions, it is taking the value higher and higher, so it is going towards infinite, because as k goes to 0, 1 by k goes to infinite, and therefore these are the sequence of functions. These are the step functions which is just going towards infinity as my k goes to 0. And that's the justification that as k goes to 0, this goes to infinite, it shoots up. Okay, and that's why you can see in the definition fk of t minus a, we wrote 1 by k and 0 in the interval a to a plus k, and here otherwise. So like as k goes to 0, this goes to infinite. So you have, and this approaches to a. As k goes to 0, this thing is a. So t is between a and a. Therefore t has to a. Okay, so t has to be a. So when t is equal to a, this is infinite and it is 0 otherwise. So therefore, what did we see? That as k goes to infinite, my fk's, okay, sorry, as k goes to 0, our fk, the step functions, they are approaching towards the delta function. This is one way to write, or another your calculus way is limit k going to 0, fk of t minus a is delta of t minus a. So you can also see delta function as a limit of a sequence of step functions. Okay, so this is one thing. Now I want to find the integration of this. So what we will do is we will find the integration of this function, and once we find the integration of this function, we apply the limit. So let's try to find the integration. So let me call ik as the integration of this fk. So my k is fixed now and I want to find this integration. So what is fk? From a to a plus k, the value is 1 by k, rest everywhere is 0. If in your book they are saying minus infinity to infinity, then also is okay. Simply replace this 0 by minus infinity, no worries. Okay, but now it is 0 everywhere. It is 0 everywhere, only here it is non-zero. So this is nothing but from 0 to infinity you can write a to a plus k only. And what is fk in this interval? It is 1 by k. You solve this, answer is 1. Well, even without integration you can see everywhere it is 0. What is the area? Integration is nothing but the area. What is the area? Length into breadth. This is k, this is 1 by k. So k into 1 by k is 1. Okay. So therefore, you take one k, you find this area, it's 1. You take another k, again the area is 1. Okay. So you fix a k, you find the integral, answer is always 1. Okay. Now we will use this fact to find the integral of our delta function. Okay, so this quantity is 1. Now what is your delta of t minus a? I want to find its integral, 0 to infinity, this thing. What is this? 0 to infinity, limit k approaching to 0, fk of t minus a dt, because our delta function is limit of fk. But what is this? This is limit k approaching to 0, 0 to infinity fk. Now here you may ask me a question that can I interchange the integration and limit? Well, answer is no. Okay, you cannot always interchange, but for some good family of functions you can do. There is a subject in mathematics called as a measure theory. When people study that theory, there you will see the justification. Okay, and step function is one of those nice function. So since this is a step function, so here I can do this interchangeability. Okay, so for this function you can do, because it's a step function, so this is allowed. Okay, limit k going to 0. What is this integral? Just now we found the answer is nothing but 1. And what is limit of constant? 1. Therefore integration of delta function is always 1. Okay, and here is the justification. Using this sequence of function, we can prove that this is 1. And why I did this justification? Instead of simply stating, it's important to know the justification. Why? Because again, if you recall your calculus, single variable calculus, where you studied Riemann theory, I will post the link in the description where I have talked more on this. What does that Riemann theory says? It says that one of the result is, if you find integration of a function, okay, some answer, say some number, okay, this is the function. If I change the function at one point, if I have another function, suppose if I have this blue color another function, it is same as the function f, only at one point it is taking different value and again it is same, then integration remains the same. That means if you find the integration of a function if I change the value of the function f at one point, and if you find the integration, you again get the same answer. Okay, so integration do not change its value if you change the value of the function at countably many points. Okay, that's what Riemann proved. And when you think of the same thing in Dirac delta function, what is Dirac delta function? At a it is infinite and rest everywhere is 0. So you can see that everywhere it is 0, so integration has to be 0, because only at one point there is a difference. Rest everywhere it is 0, so area has to be 0. But once again I said that was for those answers where the function has some value. Okay, so that those results are true when function has some value. It's not like function is taking infinite value. So that's why here those theory becomes little bit of twisted, because here we are allowing the infinity as a value. Okay, so just don't think okay whatever that you studied is incorrect or something you missed over there. No, there we had an assumption that function is taking the values at all points in the interval. Okay, and here at some point it is shooting to infinity. That's why the same theory does not apply here, and that's why when you integrate the Dirac delta function, instead of getting the 0 answer, you get 1 as an answer. Okay, so that's the small justification I always give, because you should not feel that we have taught you something wrong in your earlier courses. Okay, so that's about the integration of a Dirac delta function. Now what about Laplace? So again the same thing. So see again, what is my fk? My fk is nothing but a unit function. Sorry, it's a step function. And if you recall my lecture on unit step function, I will share the link in the description. What is my function? Whenever you have this piecewise function, you can always write in a single line by taking the help of unit step function. Okay, so what do? You take the value of the function into u of t minus a minus u of t minus a plus k. So this is the trick that I told you in my earlier lecture. Okay, link you see in the description. So it's 0 everywhere, and here the value is 1 by k. So 1 by k into u of t minus this point minus u of t minus this point. So that's how one can write a piecewise function into one single line using unit step function. Okay, good. So now we have this. So you find the Laplace. So what is of Laplace of fk of t minus a? 1 by k will come outside. What is Laplace of unit step function? E raised to minus as upon s. And here what do you have? E raised to minus. So minus e raised to minus of a plus k times s upon s. Right? So what is this? So yeah, this is a Laplace of fk. Good. Now I want to find Laplace of delta function, delta of t minus a. Laplace. But what is of delta? It is limit k approaching to 0, fk of t minus a. But again, can you interchange limit and Laplace? Because what is Laplace? It is again integration. So can you interchange integration and limit? Answer is yes, because here fk's are the step functions. So limit k going to 0, Laplace of this. What is this? 1 by k e raised to minus as e raised to minus a plus k into s whole divided by s. Now as k goes to 0, so now here we need to do little bit of adjustments. Okay, so if you observe carefully, I can take out e raised to minus as common. So this is what? Limit k going to 0, e raised to minus as, e raised to minus as. What is this? 1 minus e raised to minus ks upon ks. Correct? I simply took out e raised to minus as outside. Now again, this is not depending on k, so this will come outside, e raised to minus as. As k goes to 0, you have 0 by 0 form. So if you apply L'Hopital rule, this is nothing but e raised to minus as, limit k going to 0, derivative of this k. Okay, so I have to take derivative with respect to k. So this is s e raised to minus ks upon s. So SS gets cancelled, and as k goes to 0, this goes to 1, and therefore the Laplace of delta function is e raised to minus as. Laplace for unit step is e raised to minus as upon s. Laplace for Dirac delta is e raised to minus as. Okay, so here is the justification that why the Laplace of delta is e raised to minus as. Now this is another important property that people uses when they play with delta function. This is called as a shifting property. So if you have a continuous function g and you multiply with the Dirac delta function, and if you take the integration, answer is g of a. What a? This is that a. Okay, so to prove this equality, I need to use the mean value theorem for definite integrals. What does it say? If you have a continuous function on closed and bounded interval ab, then there exists a c in that interval such that value of the function at that point is average value of the function. If you don't remember average value, it is nothing but a to b integration h upon b minus a. So this is the theorem that I am going to use. Okay, so let us try to prove this. So my h will be in this scenario will be this product. Okay, so let us try to use this. So now let's start with the left hand side and arrive at the right hand side. So left hand side is this quantity. What is my delta? It is limit of the step functions. Now again, because of the step function and the continuity, you can take the limit outside the integral. So you have g of t into the step function. But this is 0 everywhere except in the interval a to a plus k. So I am writing this 0 to infinity as a to a plus k, and in this interval value of the function is 1 by k. Okay, now my g is continuous, this is constant, so this is a continuous function. You take this as your h of t. You apply mean value theorem to this. So what does the mean value theorem says? There exists c in the interval a comma a plus k such that h of c, that means what, g of c into 1 by k is integral a to a plus k, the function g of t into 1 by k dt divided by the length b minus a. So a plus k minus a, which is k only. Okay, and if I cancel k both side, so this integral is nothing but g of c. So this is limit k going to 0, g of c. Where is my c? It is between a to a plus k. Okay, so if I try to draw the diagram over here, a plus k, this is c. Okay, now as k goes to 0, that means this is approaching towards a. So c will approach towards a. Okay, so as my k goes to 0, my c approaches to a. And my g is a continuous function, so by definition of continuity, my g of c will also approach to g of a, and therefore as k goes to 0, your g of c will approach towards g of a. So that's a short and very nice proof of the shifting theorem for Dirac delta function that involves mean value theorem for definite integrals, and we need the continuity of g. So this is the justification. So now let me just conclude the session by giving you a small justification that why you see this phrase sometimes, that the derivative of unit step function is a Dirac delta function. Well, don't see this as per the calculus thing, whatever you have studied. Okay, this is not the actual derivative. Okay, just a phrase, or I would say is almost the derivative, I would say. Okay, let me try to convince you a little bit. What is u of t? It is 0 when t is less than 0 and 1 when t is greater than 0, right? So it's 0 everywhere, u of t. Okay, because what is u of t minus a? It is 0 before a and 1 after a. So when my a is 0, it is 0 before 0 and 1 after 0. What is delta function? It is 0 everywhere, and at 0 it shoots to infinity. Same thing one can say for t minus a, but let me play with a equal to 0. Okay, now just see the derivative of this. When here it is 0 before 0, the function is 0. What is the derivative of 0? It is 0, and here also you can see it is 0. From 0 onwards, what is the unit step function? 1. What is the derivative of 1? Is constant, it's 0. You can see here in delta it's 0 everywhere. So for t in the interval minus infinity to 0, union 0 to infinity, derivative of unit step function is a delta function. The only problem occurs at 0. Okay, so there's only 1 point difference. That's why people write this, because there's only 1 point difference. And you can see here, because see, in usual calculus way, you will say, it is not defined at 0, or you can say it's a discontinuous at 0. It's discontinuous, hence not differentiable. You cannot talk about the derivative. So this doesn't make sense. But this only 0 is only one problematic point. Rest everywhere, this is true. Okay, and here you can see it's like kind of vertical line. It's a jump. It's a vertical line, and the slope is infinite. And here also, here is infinite. So I would say, like, yeah, since there's only one difference point, therefore you will say the derivative of unit is delta. Okay, there's just one casual convincing technique for you. Another thing is to show that something is a derivative, you show that this integration is this, right? So what is integration of Dirac delta? 0 to infinity delta of t dt. It is nothing but 1. But from 0 to infinity, answer is 1. That means this is what? U of t, right? Because 0 to infinity is u of t is 1 only. Outside it is 0. So 0 to infinity delta t is 1, and 1 is nothing but u of t. So integration of Dirac delta is unit step function. So therefore derivative of this is Dirac delta function. So I hope I have convinced you, 99% I have convinced you that why the people uses this thing, that derivative of unit is Dirac delta. So yeah, that's all about Dirac delta in unit step function, or I would say that's all about Dirac delta function that one needs when they try to study differential equations. So I hope everything is clear. If you have any doubt, you can ask me in the comment section. Thank you.